Hi everyone. So welcome to Dr. Same Academy. So in the previous session, or the previous video, so I have explained you the sampling theorem. So which I mentioned it as ideal sampling. So ideal because the durations that what you got, okay, it is an impulses, okay, which means that the duration of the pulse is zero. So it is impulses. So practically obtaining such type of samples where the pulse duration is zero. So like this, the impulses you got. So it is practically impossible, correct? So even though whatever the fastest switch you take, so you get some duration. So like this. So and hence, so that practical scenario of considering sampling theorem, so I call it as pulse amplitude modulation, whereas ideal sampling was impulse. Okay, so for your details I will share the links in the description about the ideal sampling as well, so you can go through that. So now let us start with pulse amplitude modulation. So what is this pulse amplitude modulation is? In pulse amplitude modulation, the amplitude of the carrier signal, so carrier signal is a train of rectangular pulses. So the amplitude of the carrier pulses varies in accordance with the message signal. So it is called pulse amplitude modulation. As we know what is amplitude modulation, it is varying the amplitude of the carrier. Now here the carrier that what we are taking, it is in the form of pulse, and hence pulse amplitude modulation, the name. Okay, so now let us understand this with this diagram. Suppose if I take the pulses as a carrier signal, so this is one pulse, this is the other pulse. Okay, so you get so many pulses, a train of pulses like this. Okay, so the amplitude of carrier is constant, but in the modulated wave, if you see, the amplitude of the carrier signal is varied in accordance with the message signal. This dotted line indicates it is a message signal, whereas the amplitude of the carrier is changing with respect to message signal, and hence the name pulse amplitude modulation. This M of t, I call it as a message signal, and this is the modulated wave. The solid waveform indicates it is a modulated wave. So in this type of modulation, that is in pulse amplitude modulation, the pulse duration is held constant. If you observe the duration of the pulse, so this, the duration of the pulse, every pulse, if you look, it is constant everywhere. And so this is the waveform of pulse amplitude modulation. So in the figure, the pulse duration, whatever I consider, this is the duration of the pulse. So the pulse duration what I consider is t, or generally we can also write it as tx. Okay, so this pulse duration t is very small when you compare with the sampling duration. Okay, so that means the distance or the time from one sample to other sample. Okay, so this duration is larger, and whereas t is very small when you compare with ts, because of which what happens, so you require a more bandwidth because you are transmitting the information only in these portions, whereas in these portions there is no information sent. Okay, so you are wasting the bandwidth. So the bandwidth requirement of pulse amplitude modulation is very more when you compare with the message signal bandwidth. Okay, so if I want to give the relation between them, so the signal that what we are transmitting is this. Okay, whereas so the bandwidth required is very large when you compare with 1/bt, or in general, so the bandwidth requirement is very large when you compare with the message signal bandwidth. Anyhow, this is a disadvantage of pulse amplitude modulation, but so we let us understand pulse amplitude modulation better with mathematical expressions. So as the transmitted bandwidth so is very much high, so this can be reduced to a small extent by using standard pulse, which system is capable of transmitting. Okay, we will use the standard pulses so that the transmission bandwidth can be reduced. So now if I want to represent this mathematically, the modulated wave, the pulse amplitude modulated wave, I represent it as S of t. So which is equals to, so summation n ranging from minus infinity to plus infinity g of nts, that is samples of the input signal. Either I can write g here, or so since the waveform indicates m is the message signal, you can also write it as m, or so I will call the message signal as g of t. So g of nts are the samples of the message signal multiplied by v of t minus nts, that is the rectangular pulses, that what I am multiplying with g of nts. Whereas in ideal sampling, what we have seen, it was g of nts into delta of t minus nts. Now I am not using delta of t minus nts because I am considering practical scenario where impulses, creation of impulses is impossible. Okay, so therefore, so I can represent S of t in equation, so in this equation, where g of t are the samples of g of t, the message signal, and ts is the sampling period as indicated in the diagram, and v of t is one pulse, rectangular pulse. Okay, so with this the modulated wave, so I can represent the pulse amplitude modulated wave. Okay, so now let us take the duration of the sample as t, and the sampling rate fs is equals to 1 by ts. Okay, so ts if I choose equals to 2w, okay, sorry, 1 by 2w, then fs will be equals to 2w. Let h of t be the rectangular pulse, okay, of unit amplitude and duration t. I will consider one rectangular pulse, okay, whose amplitude is 1, and the duration is t. So such type of rectangular pulse I represented as h of t, and this has to be multiplied with g of t, that is the input signal, so that you get what is s of t. Let me represent this h of t graphically. So if you look here, so this is your h of t. So it is a rectangular pulse whose amplitude is 1 and the duration is from 0 to t. So whereas in ideal sampling, I considered the ideal means impulses, the ideal behavior. Okay, so where the duration I assume to be 0, but practically since it is not possible, so I now in pulse amplitude modulation I have considered a pulse with width from 0 to t. Now I will rewrite the expression. So s of t is equals to summation n ranging from minus infinity to plus infinity, the samples of the input signal multiplied with the rectangular pulse h of t minus nts. Since all these samples has to be multiplied with the pulses, so this is h of t. I will shift this for every interval of nts. Okay, so this is the representation of h of t, and hence we got so the modulated signal. So if you look at this h of t, so I can say from between the interval 0 to t, the amplitude is 1. So therefore can I write h of t is equals to 1 when between 0 to t, whereas the other limits after, that means greater than t, means this duration, or less than 0, this duration. So what is the amplitude? It is 0. Therefore it is indicated h of t is equals to 0 when t is less than 0 and also t greater than capital T. Okay, so all these durations h of t is 0. So this is nothing but, okay, a rectangular pulse. Therefore I can replace h of t as a rectangular signal. Okay, so now let us take an instantaneous sampling. So we already derived instantaneous sampling in the previous video, so that we we obtained the equation, the sampled wave g delta of t is equals to summation n ranging from minus infinity to plus infinity g of nts into delta of t minus nts. This was the equation, sampled wave, what we got for ideal sampling. Okay, so now what we do, so instead of delta of t minus nts, so I have h of t, correct, the rectangular pulse. Okay, let it be. So now considering delta of t we know, so let me convolve g delta of t with h of t. So h of t is the rectangular pulse. Now if you convolve these two, so we know the convolution formula, the convolution of the two signals, so can be represented as integration of minus infinity to plus infinity. So that is the convolved signal, that is g delta of t, the first signal. Okay, so into, so shifted version of the second signal, that is h of t minus tau into d tau. This is the convolution formula. So if you want to convolve two functions or two signals, then this is the formula, standard formula used. Now, so right hand side, substituting for g delta of t from equation 4. So if you substitute the value of g delta of t into this equation, okay, so I get it as, so integral minus infinity to plus infinity as it is, summation n ranging from minus infinity g of nts into delta. All this is nothing but your g delta of t. Okay, so I will retain this h of t minus tau as it is. Okay, so this is g delta of t convolved with h of t. So now, so interchanging the summation, same equation I have written, but integrals I have brought it outside. In other words, summation I brought it outside or integral inside this. Therefore, exchanging them, so we get summation n ranging from minus infinity to plus infinity. So that is the samples g of nts into integral of delta of t minus nts into h of t minus nts. What is delta function? You know, that is at t is equals to mentioned value. So you have a delta function. Delta function means whose amplitude will be 1 only at that particular instant. So when you multiply 1 with any function, you get the same function, right? So when you multiply 1 with any function, you get the same function, but you get the shifted version. Therefore, so I can write the convolution of this will be, so these two terms I'll write it, summation of g of nts as it is. So when you multiply 1 into this function, you get the same function, but it is shifted at every nts. Okay, so this is convolution of these two signals. Now what is this convolution? That is multiplication of your g delta of t into h of t is nothing but, so your modulated wave, right? So I write it as, from the previous equations, g delta of t into h of t is nothing but your s of t. Okay, so now, so this is your modulated signal or pulse amplitude modulated signal in time domain. So if I want to represent in frequency domain, what I do, take the Fourier transform. So s of t becomes s of f, g delta of t becomes g delta of f. So convolution in time domain becomes multiplication, and so h of t becomes h of f. This is your h of f, not g of f. Okay, so let us rewrite that expression. So we know that from the ideal sampling, we already derived g delta of f is equals to fs into summation n ranging from minus infinity to plus infinity g of f minus nfs. We know this expression from the previous video. Okay, so we have derived this. So now, so how does this pulse amplitude modulation looks like is, the output, the sampled wave or the modulated wave, s of f is equals to fs into g of f minus nfs. Okay, this will be as it is. You got only this much in ideal sampling, because so the pulses that what we considered is impulse, that means pulse width being 0, okay, and amplitude is 1. Therefore 1 into you get the same function as this. But now I don't have impulses, I have pulses. So therefore I have to multiply with its own rectangular pulse frequency domain of that, which is called as h of f. This is your pulse amplitude modulated wave in frequency domain, and I have given a comparison between ideal sampling and pulse amplitude modulation. So this is, so if I ask you explain what is pulse amplitude modulation, so you can define what is pulse amplitude modulation. So you can draw the diagram, means waveform of it, and also mathematically you can derive. So now there is one major drawback of pulse amplitude modulation, that is called distortion of pulse amplitude modulation, which I call it as aperture effect. As we know, so we have used h of t, which is a rectangular pulse rather than using impulses. So if I know the frequency domain representation of h of t, that is h of f, this is how it looks like. So h of f is tau into sinc function. So if you remember the waveform that I have shown, this was your rectangular pulse, and what was the frequency domain representation of that is, so it used to be like this. So amplitude keeps on reducing, correct? This was the spectrum you have seen in the previous slide. Okay, so that is what we call it as sinc function. So we call it as sinc function. This is the transfer characteristics or the frequency domain representation of your h of t. This is h of t, whereas h of f looks like this. So what is the drawback of this is, at lower frequencies, so this is 0, at lower frequencies amplitude is maximum. But as the frequency increases, what is happening to amplitude? It is decreasing. It is rolling off to 0. So in such cases, so you cannot apply this PAM for high frequencies. So therefore, so what we do, okay, anyhow, this effect we call it as aperture effect. What is aperture effect is, at lower frequencies we get the maximum amplitude. As the frequency increases, the amplitude is decreased. Okay, it rolls off to 0. Such type of effect or the distortion, we call it as aperture effect. So this is the transfer characteristics I was talking about. This was h of t, whereas h of f is, you can observe that the amplitude is reducing when the frequency is increased. So this effect I call it as aperture effect. So next question is, how can you compensate this aperture effect? So to compensate this, so we will go for the technique called, okay, so equalizer. So I use, this is your modulated PAM signal. At the receiver, we know that we have to reconstruct. I need to get back the original signal. So if you want to get back the original signal, I go for a reconstruction filter. So once a signal is reconstructed, so it is distorted because of the aperture effect, and therefore I should use equalizer to compensate. So what does this equalizer consist of is inverse of sinc function. So we had sinc function in the aperture effect. So in the compensation, what I do, I take inverse of it, so that sinc get cancels, so you get a constant output. Okay, so that the message signal what you get g of t, okay, even though if it is slightly higher frequencies, so you don't get any distortion because of the equalizer. Okay, so this is about the how you can compensate about aperture effect. Now let us see. So we understood what is pulse amplitude modulation, how mathematically this can be represented. The distortion in pulse amplitude modulation is aperture effect, and how to compensate this is we use equalizer after reconstructing your signal, where the characteristics of equalizer is inversely proportional to sinc function. Okay, so now let us look into the other disadvantages of PAM. So the PAM disadvantages are PAM requires very large transmission bandwidth. In the very first slide I told you that pulse amplitude modulation requires more bandwidth. Okay, so the bandwidth requirement is very large when you compare with the message signal bandwidth. The reason is, so you get only pulses in a certain time duration, the other time duration channel is idle, it is not transmitting, therefore you require more bandwidth. Okay, so the other important disadvantage of FAM is, so there is more interference of noise, because the amplitude keeps on varying. When the amplitude is varying, definitely, so the noise accumulation is more, so you get a more noise. Okay, so and the other one more disadvantage is, since amplitude of PAM signal varies, so according to definition of PAM, what is it? Amplitude of the pulses varies with respect to message. As the PAM varies, definitely the peak power requirement is also varied. Okay, so you cannot design a exact particular transmitter, okay, whose power requirement or the power required is constant. Okay, so it keeps on varying, therefore it is a little bit difficult to design the circuitry. So these are all the disadvantages of pulse amplitude modulation. So the ideals, this is the practical sampling tech. Pulse amplitude modulation is practical sampling theorem. So whereas the ideal sampling theorem is considering delta functions. Okay, so however these disadvantages of PAM can be eliminated, that is bandwidth requirement, all those can be eliminated by multiplexing the signals. Wherever the channel is idle, so what I do, I can multiplex the other signal so that one more signal can be grouped and can be transmitted. That is called by using multiplexing, either TDM or FDM, so we can perform and do it. Okay, so that we will see it in the next video. So thank you for watching the video. So if you like the video, kindly like, subscribe, and if you have any clarifications required, so kindly comment in the video. Thank you.